Last class, we have seen this problem and we have learned how to find the deflection at E where the point load is acting according to Castiglione's theorem 1. We have calculated the strain energy stored in each and every member. We have summed it up and we have differentiated partially with respect to the load applied at E to obtain the deflection, vertical downward deflection at E. This we have seen in the last class. Now, I'm going to take the same problem to find the deflection at some other point. Okay, not at E, at some other point, how to find the deflection with the help of unit load method. Okay, with the help of unit load method, how to determine the deflection. So now let's go to that problem. So this is the problem. Find the vertical deflection at C. So assuming X modulus to be 200 gigapascal and the same cross-sectional area for inclined members 1000 mm square and for horizontal members 800 millimeters square. Now it is required to find the vertical deflection at C. Earlier problem we have got the deflection at E where the load is acting. Now at C the load is not acting. Okay, so let it be any number of loads acting on a structure. Let it be any number of loads acting on a structure. Okay, we don't have to bother. With the help of unit load method we can easily get the deflection at a particular joint. Okay, at a particular joint. Okay, now the joint is C. At C, I have to find the deflection. So the now first procedure is for the given external loading, we have to calculate the forces. This, since we have done already in the previous problem, just I have noted down all the values and entered in the table column. Okay, these are the members. Against the member, I have entered the force values, all the force values. Okay, this is the length and this is the individual areas and this is the X modulus. So X modulus is constant. You can introduce or you can omit this column also. Okay, so it is very, I mean, it is good to introduce that column and keep the values, numerical values in the table column itself. And now the next step would be remove all the external loadings that are acting on the beam, sorry, that are acting on the truss. Apply a unit load at a point where the deflection is required to be calculated. Where the deflection is required to be calculated. Okay, so now, so this is the joint C. I have applied a unit load 1. Okay, unit load. We are taking moment about this. Find the support reactions. We got the support reactions. Then taking a joint B, we are resolving the forces, getting the forces in member BE and BD. BD and BE. Okay, compression, tension. Then we go for next joints D and A. So at joint D, FDC, FDE, we apply the force, and joint A, FAC and FAE obtain the forces. Then FC, joint C. Okay, at joint C, apply the force 1 Newton, which is already applied in the structure. Then find FCE. Enter all the values which we obtained when the unit load is applied. Okay, so when you are calculating K means K values, you have to remove all the external loadings. You have to apply a unit load where the deflection is required to be calculated. This is only for the external loadings. Okay. So now formula is PKL by AE. Formula is PKL by AE. For individual members, you have to find out PKL by AE. Sum it up this column PKL by AE. Okay, that will give you the deflection at the point C. There is a vertical downward deflection at C. 21.6 into 10 power minus 6 P. P should come. Okay, I missed P in this column also. P should come here. Okay, so add P here, and here in this expression also you'll get P here. So now we are going to the redundant frames, okay, where the, for example, if you take a condition m is equal to 2j minus 3 means perfect frame, m is less than 2j minus 3 means it's a deficient frame, m is greater than 2j minus 3 means it's a redundant frame, where m is the number of members and j is the number of joints. If you apply that concept here, you will get m is greater than 2j minus 3. So m is nothing but number of members, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 members, and joins 1 2 3 4 5 6. So 12 minus 3 is 9. So members 10. So 10 is greater than 9. Your difference is 10 minus 9 is 1. So it's a single redundant structure, I can call it as a statically indeterminate structure. We cannot directly solve the statically determinate indeterminate structure. Okay, first we have to convert the statically indeterminate structure to statically determinate structure. So let me remove any one of the members so that the structure becomes statically. Now I have removed the member FC. Now the given structure becomes statically determinate. Now for the given loading, find the support reactions. Okay, RAB, RAD, RAH is 0 as it is in support. No horizontal or inclined loads are acting. Now, if I take this as theta, theta, whatever it is, sine theta 3 by 5 and cos theta 4 by 5, hypotenuse is 5 because root of 3 square plus 4 square. So now we can see the joint A. Okay, I've taken the joint A. So we're resolving the forces. We are finding the forces FAB. Resolve sigma Fx. We find the force FAF. T means tension, C means compression. Take the joint F, draw the free body diagram, find the forces. Okay, so tension force. This is also tension force FFB. And joint D, resolve it. And compression force. Okay, you know the sign conventions I have told you already to be followed while solving sigma Fy is equal to 0, sigma Fx is equal to 0. Then we have found all the forces. Okay, now at the joint C, so this is the forces. I've got these forces. Okay, joint B. Okay, now enter all the values in the tabular column, members, and these are the forces acting on the member due to the external loading, length of each member, area of each member. Now we have removed a member FC. Okay, in that location, introduce a unit load acting 1 kilonewton away from the joint F and 1 kilonewton acting away from the joint C. Okay, in the same direction of diagonal member, in the same direction or same inclination of the diagonal member CF. Okay, so with this unit load, you have to find the support reactions RD, RAV, RAH. Then for these support reactions values and unit load, you have to find the member forces by drawing the free body diagrams. Okay, after obtaining all these values, enter into the tabular column K values. All those values are called as the K values. So P, K, L, A. Okay. So here you can see X is the redundant. Let X be the redundant. Okay. Formula is minus sigma PKL by AE divided by summation of K square L by AE. Since in this problem E is constant, we can get cancelled that E and summation of PKL by A divided by summation of K square L by A. So introduce the column PKL by A and K square L by A. Okay. So get this X value. Okay, X value. S is equal to P plus XK. Okay, so this is X value. S is equal to P plus XK. For example, remember AB. P value is this. X value is this. So minus 88.8 plus of minus 4.37 into 0. You will get this value. Like this, for each and every individual member, you can calculate S is equal to P plus XK, where this column gives you the actual member force for the given statically indeterminate structure. Suppose if each and every member is having different Young's modulus value, means you have to introduce a column for Young's modulus. So Young's modulus. So here you will have a like a PKL by AE and K square L by AE. Okay, you have to use this formula to get the redundant. Okay, here in this problem, Young's modulus is constant. Thank you.